I'm going to hit play on this, and I want you to guess what this is. Okay, got a bunch of little like lines that are going along. You can see that they're graphed out here. I can like scroll through, so there's a bunch of different things here. Can you guess of what each of these are? You guess. Tell the person next to you. What are these lines? What do these lines represent? Okay. Any thoughts? What are these? Yeah. What is this? What are these? Yeah. Yeah. Sure. Radio waves. Absolutely. What does a single line represent on this? Each line here and each thing, this represents all of the different Bluetooth devices that my phone is able to see right now, which is like kind of crazy. Like there's a lot. There's like a few hundred here. Pretty cool, right? I mean, it makes sense. Probably like each one of you maybe you have like a laptop with Bluetooth, maybe a phone with Bluetooth, maybe like headphones with Bluetooth, maybe an Apple Pencil with Bluetooth, maybe like a mouse with Bluetooth. Like maybe each one of you has, on average, maybe like 3 devices. Now imagine how many people are within like a tenth of mile radius of here. There's probably like easily 1,000 devices all at once that are trying to like advertise out and transmit things out over Bluetooth all at the same time. And yeah, my phone is able to kind of seamlessly just deduce each one of them. Notice a lot of them are labeled as NA, and this is most likely because it's maybe like changing its ID as like a form of security. So it advertises like one thing, and then it changes its ID, and then advertises it again. If I had like connected to this device listed as NA, then maybe it would like de-obfuscate it, and it would make it actually clear what this device was. For example, I think we can even see my headphones here. Yeah, so here are my headphones, and so you can see, I guess it's not transmitting anything right now because they're just in my backpack somewhere. Yeah, okay. Well, I guess the question is, how is this possible, right? Because we've been using I2C, and that has just been like one single wire. And the idea is that on this one single wire, only the host can send out data, or one of the peripherals can send out data. But if you ever have 2 things that are trying to like write a 0 to the I2C bus at the same time, then you'll probably it'll be corrupt and you can't read the signal anymore. Like you can only have one thing talk on that wire at one time. So how is it that we can have in the air around us, how can we have so many distinct signals where my phone is able to pick up each one of these different devices? How is this possible? How is my phone able to deduce all of the different devices and peripherals that exist in the air? Yeah. Okay. Ponder this for a second. I'm going to show you a different demonstration. Okay. So this is a sound analyzer website that I found. So notice if I hit play, this will actually show me the current. It shows me like a graph over time. It's like kind of the amplitude over time of my microphone in my computer. And the way microphones work is it's like a little kind of levitating magnet, or maybe like a coil or something. And as someone speaks, as it picks up sound waves from the air, it will vibrate. And as it vibrates, there will be little coils around it that will measure the amplitude of the vibration. So here, like if I'm talking like louder, you can see that there's more amplitude. And if I talk softer, yeah, see it. It's less of a vibration on the microphone right here. Yeah, the more you talk, the bigger the amplitude. The less you talk, the smaller the amplitude. Okay. There is. You can also see up here that it is deducing out all of the frequencies that goes into this microphone. So if I wanted to like whistle, so right here, you can see it made a big old spike right where it noticed that there's a large amount of there's a large amplitude at that moment of where it realized that there was like a, I don't know, that like the microphone was oscillating at a constant frequency. So I'll do it again. So right here, you can see that it looked like at about, actually, let me see what, is that 1 kilohertz? Yeah, so about like, whatever, 1,000, whatever, 130 hertz. The microphone is like most likely to oscillate at that period. But also, it will also oscillate at like higher harmonics as well. It'll also oscillate at lower harmonics. So it is just a fact of life. It's kind of just like one of the cool just things about the universe that we live in, that it just so happens that any wave like this that a microphone will pick up can be broken down into all of the like component sine waves that make it up. So what you could do if you wanted is, instead of like keeping track of every single like tiny like amplitude over time like position of your microphone, instead what you could do is you could also just keep track of all of the different frequency components of your microphone. So you can see like how fast is it moving like in this specific frequency, or how fast is it moving in this specific frequency. Okay. Has anyone seen kind of this before, the idea of decomposing a signal into like its component frequency parts? Okay, so hopefully I'm not introducing this to you for the first time. If you've ever taken a signals course, you'll probably spend like a few weeks on this. You'll learn like the fast Fourier transform algorithm, and you'll do fun stuff with this. But what we can do is actually take advantage of this and use it for communication over the air, which like the air you can think of as just like one big wire. And so what we can do is, in the air, like in this one big wire, so we can actually send out multiple bits of information, because we are able to decompose these waves in the air into like frequency slices. Okay, I'll give you an example of that. Okay, so here I have a signal A, and you can see I'm currently just encoding the value 37 in binary, or in hex, I guess. So this is 37 in hex. Here's B. This would be, I guess, like 9, 7. Okay, so here are my two signals, and my question now is, how can I transmit these two signals through the air in a way that they both can be like read in through an antenna and then both like deduced out? Maybe one idea is maybe you could have like one person with like a really high-pitched voice. Maybe they could just kind of go quiet when they want to transmit zeros, and then when they want to transmit like ones, maybe they start speaking in that high-pitched voice, and then they stop for a little bit, and then they go and transmit the last few bits by speaking in the high-pitched voice again. Maybe you have someone else, maybe B is like a low-pitched voice. Maybe B says like in a low voice, transmits a 1, then at the same time transmits like then goes and doesn't say anything, then says something in a low voice, then doesn't say anything, and says something in a low voice. And then what you'll hear is the combination of those voices at the same time. So you can very clearly pick out, it's like, okay, the high-pitched person is talking, and like here the low-pitched person is talking. So you can end up deducing out like what their like combination is at any time. And I demonstrated this by showing, so if we have a flat line on this red signal, that means that there is like no noise coming out. And then if we have an oscillation, that means that there is noise coming out. So here you can see it's oscillating a little bit slower than like this signal right here. So this signal, it's oscillating a little bit faster, and then here it means no oscillations. So okay, so question to you, is this going to sound like a higher pitch noise or a lower pitch noise compared to this blue one? Which one is higher? Is the red pitch going to be higher, or is the blue pitch going to be higher? Yeah, the blue pitch is going to be higher because it's like the frequency is higher. Yeah, it's like it's happening, it's oscillating more often. Well, what we can do then is, as we transmit out these signals into the air, well, then the combination of them would be this purple signal right here. And we can just very clearly just look at it and deduce out what like both the A signal and the B signal is. So here, we can see that we just here have the high frequency, okay? And then we have neither of them, Then here we have the low frequency. Then here we have both of them. Then we have neither. Then for the rest, we have both of them. Cool. Yeah, right? So you can also imagine that maybe you could expand this out. Maybe you make like another signal that is now even a higher pitch. Now you can deduce out the higher pitch just by kind of looking at it. And there are cool algorithms and hardware. There's really like kind of fancy analog circuits that can like perfectly kind of pick out each of these frequency bands for you, and will convert this into like what bits are being sent on what frequency channel. Pretty sick. Okay, I'm gonna just make sure that you are all understanding. What I want to do now is I have this other signal right here, and I'm not showing you what the values of A and B are. Or I guess I'm showing you the red. Wait, hold on. Close your eyes for a second. Okay, hold on. I want to actually do minus 2. Okay, that's what I meant to show you. Okay, so now I gave you this signal, and I did not show you what A and B are. Assume that maybe A is the lower pitch one, and assume that A is the lower pitch one. Assume that B is the higher pitch one. What I want you to do is take a second and decompose this signal that maybe is being transmitted out into the air. Decompose it into A and B, which should just be like a list of ones and zeros. Okay, go and spend a minute on that. Let's say together in order from left to right. Let's say in order what A is sending out. Okay, so first we have 1, okay, then 1, and then 0, then 0, then 1, then 1, then 0, then 1. Yeah, perfect, okay. And then let's do B. So first, 0, okay. 1, and then 1, 1, 0, 1, 0, 1. Cool, fantastic. So now you have just deduced out these two signals from this, this compound signal right here, the combination of two. And if we go and look, actually, then that is in fact what I had written out ahead of time. Cool, yeah. Sick. Okay, so I guess maybe the way that I kind of introduced this lecture is that maybe you're imagining now, it's like, okay, so now I think I have an idea of what's going on. So now I know that there's like a mini speaker inside each of our phones that is sending out like this noise that maybe we can't hear as humans, and then we have other like peripheral devices that are then listening to these noises and are able to decompose this, the compound noise of like all the 100 devices talking at one time, and is able to decompose them into each of the frequency bands just kind of by looking at the frequency and saying like, okay, is there a component of that frequency at that time? And if so, that's a 1. If there's no component of frequency at that time, then that's a 0. And okay. So actually, phones do not use mini speakers that play like high-pitched noises. Does anyone know what instead these waves represent? Like what is like this wave that's being sent out into the air? Yeah. Yeah, exactly. So this is a radio wave, and kind of it's an electromagnetic wave. So in the air around us, there are oxygen atoms, and each oxygen atom will have valence electrons and just electrons in general. And it just so happens that anytime that you flip a switch or something, or anytime you oscillate some sort of large piece of metal, that what will happen is if you increase the voltage, decrease the voltage, then the electrons around that big metal object, the electrons in the air, are going to start to vibrate, and they will put off electromagnetic waves. They'll put off electric fields, and as the electric fields change, then you have magnetic fields that change, and then electric fields that change. I won't get too into it, but basically what's happening is as you have some big metal thing that is oscillating between a voltage, you actually get like electrons in the air that will oscillate and will vibrate. And they will vibrate so much that you can have some other antennas like way far away, and if it just sniffs like in the air, it can actually pick up the electrons that are vibrating around it. And now that big like metal rod somewhere else is now able to actually see what the like metal rod over here was transmitting out. So as a metal rod maybe over here is transmitting out some data, just by electrons vibrating in the air, the signal will eventually get over to the other like antenna that's maybe sitting over there. And that is how that's how antennas work. You just have some voltage that's oscillating on it, and just by like magic, it just appears now in any other kind of antenna that you sniff around. Yeah, so that's what antennas are. And and so that is how radio works. That's how electromagnetic waves work. It's just electrons vibrating in the air, and then you are able to like pull apart that compound signal, and it's going to be pretty noisy. There's going to be a lot of things communicating through the electrons, or maybe just electrons just vibrate in general. So maybe you're not sure, like, is that a human generating that signal, or is that just like random noise from the electrons just wiggling? But somehow there's some, you can use algorithms to just deduce out and figure out, it's like, okay, actually, that is like a Bluetooth device that is sending things out into the air. Yeah, okay. Pretty sick. Yeah, question.
So in this example, like each bit is like 1x long, right? Does that make sense? Like, it goes to 8 because you're communicating 8 bits of data.
Correct.
What, like the real world, what determines that size of that x? Like, is it like 10 like nanoseconds determines like if it's on for that amount of time, and that's a bit?
Sure. So you're just asking like, how do we tell the rate of like, how do we tell the bit rate?
Yeah.
I guess. Yes. What you. So it's actually very similar to UART in that I covered whenever that was, maybe last class. UART is kind of similar in that you only have one single wire, and that wire is just set at like a fixed baud rate. And so like both the transmitter and the receiver must agree ahead of time on the speed. So maybe they just agree. It's like, oh, you know what? We will just say data will be transmitted at like 1 gigahertz or something. So they just know that this like width right here is maybe 1 nanosecond. So they just agree ahead of time. And now with more complicated things, with like Bluetooth and Wi-Fi, actually what will happen is it will probably it will have some fancy algorithm of detecting. It will probably just be able to tell like how fast the data is being sent out. I'm not sure the exact algorithm that they use, but they are able to just kind of sniff the air and figure out exactly what frequency the like bits are being sent at. But it's very similar to UART in that there's like specific baud rates that the data is able to be sent at. Very good question. Sure. Any other questions with this? Is this blowing anyone's mind right now? When I like first learned this, I was like, wow, that's crazy. Okay, good. So, by the way, I posted the Desmos chart right here. I posted this on Canvas, so you're welcome to play around with this if you want. You can see what happens when you try adding like more channels, more frequency bands, trying to send more signals. You test out you test your friends and see if they could figure out like what the compound signals are encoding. Okay. I also posted this slideshow provided by Jose Renau, the previous instructor of the course. Really like these slides, so I wanted to go through a few of them. Okay. So there. So as I said, right. So electrons wiggling. That is basically just what electromagnetic waves are. It's kind of interesting though, because there are actually rules on how fast us as just humans living in the United States are allowed to wiggle the electrons in the air. There are regulations on that. It is not allowed for you to just set up like an antenna, like set up some big like metal pipe and just pass in like any like high frequency signal that we want. Like it is just disallowed. And if we want, we could like look through and actually see like, so here is the official like United States frequency allocations. And so you can look in this and you can see like, yeah, some of this is like reserved for like military use or like broadcasting television. So if you wanted to like really screw with like the broadcasting networks, what you could do is like just set up a, like you could find this frequency, which seems to be about, I don't know, yeah, 50 megahertz or something. So you could just attach like a super high powered oscillator up to just a big metal pipe and broadcast it out at 50 megahertz. And then eventually you'd probably like have cops showing up at your door and they arrest you. And that's a true story. Yeah. So you are genuinely not allowed to like oscillate electrons at certain frequencies. And but the frequencies that you are allowed to oscillate at, so you can actually see here, it does recognize that there are some bands that are considered amateur frequencies. So you are allowed to broadcast at these frequencies. So you can see like, okay, so here it's like around 6.8 megahertz and whatnot. But probably the most useful band of frequencies that you can oscillate at are this section right here, which is about 2.4 gigahertz. Okay, anyone heard of like 2.4 gigahertz just in their life? Maybe you've set up like a Wi-Fi network at your apartment or something. And oftentimes you'll see something that's like oh, set up like a 2.4 gigahertz Wi-Fi connection or set up a 5 gigahertz Wi-Fi connection. So 2.4 gigahertz for a while was just kind of like free reign, and almost every single country agreed, like came together and they agreed, and they were like, you know what, 2.4 gigahertz up to about 2.5 gigahertz, that is free reign, and any company is allowed to just do anything that they want on 2.4, 2.5 gigahertz, including this cool like creator of, and I don't remember his name, but the inventor of something called Bluetooth came along and was like, you know what, this 2.4 gigahertz range, I really like this, and now I'm going to start developing hardware that will like send out data at 2.4 gigahertz, and then I'll also create like receivers that will receive that data at 2.4 gigahertz, and then we can use that transmission for things like like headphones or computer mice or whatnot. And yeah, so it also happened that Wi-Fi was also becoming popular around that time. So Wi-Fi is also kind of overlapping in this 2.4 gigahertz. Wi-Fi became much more widely adopted than Bluetooth, though. So Wi-Fi actually later on was able to grow and now takes up all the way up to like 60 gigahertz. So a lot of like this range is also Wi-Fi, 30 gigahertz. Yeah, so pretty sick. Yeah. Any questions on this? You can look up like all of the different like allocations for anything. Yeah, as engineers, sometimes you want to use like different parts of the frequency band. Sometimes you want to use other parts. Sure. Okay. So you may notice here. So here, this is showing the wavelength. So that the distance between like a single oscillation of an electromagnetic wave. And so all the way over here, this is, okay, pop quiz. What band of frequencies is this part right here? What is the frequency number? It's, 2.4 gigahertz right here. Yep. And then also you can see like all the way over here, you actually get visible light, which is kind of cool. So actually, if you had like a Bluetooth signal that maybe you wanted it to now oscillate, what is that, 1,000 times faster? So if you take a Bluetooth signal and actually just, take the exact same kind of hardware, so it's just an antenna, and now you oscillate it, 1,000 times faster, then now you get visible light. And that's actually what like LEDs kind of do, is LEDs, it's just an LED, it's just a light emitting diode. So it's just a diode where you have like a P-type and N-type substrate kind of connected to each other. And the rate at which the holes and electrons like combine into each other is roughly equal to just this frequency. And so therefore it emits out the like oscillations of the electromagnetic waves at visible light. That's how LEDs work. Yeah, pretty sick. And then also like way past that, then we got UV. Okay. What is significant about UV? Yeah, so this is ultraviolet. What is like kind of the main thing that UV does to humans? Yeah, right, skin cancer, right. So, and then past that, you got X-rays, which gives you like kind of more advanced cancers. Yeah, no, yeah, absolutely, right. So, so you actually have a limit of how fast you want to be wiggling these electrons in the air around you. If you wiggle the electrons too fast around you, then it will knock away like parts of your internal cells and it'll cause cancer. Yeah, but also notice like all the way. So okay, so we have like X-rays that cause like mega cancer, and then we have UV that causes like skin cancer. Then we have visible light, which probably also is not great. Let's keep our voices down. Then you have infrared, which is basically just heat. Then you have microwaves. Then finally, all the way over here, you have like 5G. So okay, so therefore, when you're hanging out with your crazy uncle and he's like, oh, 5G is causing cancer, you can be like, actually, like we're like 1,000 times weaker than like UV in that. Yeah. So you can argue with him about that. Oh, cool. Okay. I will say another thing though. So yeah, notice that there are like high frequency signals. So apart from just causing cancer, what is like another reason why maybe? Let me rephrase that question. So there are different benefits of different frequencies when sending out data. So like in this, so in this like graph right here. So in this graph, we can see that, the 2.4 gigahertz range is like right around here, but we can actually send out data and like a higher speed, like signal out over here. What are some like pros and cons of sending out data on a lower frequency band compared to sending out data on a higher frequency band? Okay, think about this for a second. Maybe you already know. Maybe go and explain to the person next to you. We'll reconvene in like 20 seconds. What is a benefit of sending data out on a low frequency band, and what is a benefit of sending out data on a high frequency band? Okay, so what is a major benefit of sending out data on a higher frequency? Yeah. Range. I would disagree with that. I would say that's actually a benefit of sending out data on a low frequency. Okay, yeah. So what is the major benefit of sending out data on a high frequency? Yeah. It is faster. Why would it be faster though? Yeah. Yeah. Okay. Well, let's pull up Desmos again. Let's see if I can quickly make a demo of this. So here we can see that the data rate is actually sorry. The data rate is quite a bit slower than the signal rate. You can see the signal is like oscillating several times before it actually like finishes sending this bit. So this will give a lot of resolution, and there's a lot of time. There's like several cycles here for the for whatever like receiver. There's a lot of time for the receiver to properly deduce out what this bit is. Now let's see what happens if I go and let's see what happens if I go and decrease this frequency. So if I now maybe set this to maybe 2. Okay, so now the frequency is only, it's only 2 hertz, I guess. And so here you can see it just barely completes like half an oscillation in the time for it to send one single bit. Or here, if I set it even lower, so if I set it to like a really low frequency, maybe like 0.5, you can see it actually doesn't even complete like a full oscillation. It like barely does any sort of oscillation. And so the slower your frequency, the slower you also need to make your baud rate, because there's just not enough like oscillations per bit. So if you want like really good resolution, you actually want to send it out on a higher frequency. So if I sent it out over like 30 times, you can see that it's oscillating several times just in one single bit being sent. Yeah, so sending out on a higher frequency actually gives you better resolution. It's actually easier to sniff out that line if it's on a higher frequency. Okay, why is sending out on a higher frequency maybe not always the best? Okay, yeah. Absolutely, definitely. More power. That's a huge thing. Just the crazy analog circuitry that goes into oscillators. As you increase your frequency, the oscillators will need more power in order to create like a better signal. Absolutely, yeah.
Does the signal decay faster when you go over?
Absolutely, yeah. So that's kind of the big thing is the attenuation through the air is much more significant with higher frequencies, and especially like through like solid walls. Like you may have like if you're like standing outside and you have like it says like 5G connection. You're like man like I have great connection. The second that you go behind a tree or something, or the second you step inside, maybe it drops significantly. Now you only have like, maybe you had to reconnect to some other frequency band because it has blocked all of the like 5 gigahertz band. Yeah, that is kind of the major problem with sending out data on a high frequency is for some reason, it just like attenuates faster. It just decays faster. And so you need almost like direct line of sight anytime you're using like a high speed frequency. And that's actually like why you will sometimes have you'll have like satellite dishes that will point like directly at each other. It's because they need like a direct line of communication between them because maybe they're sending out their data at like super high frequency. Maybe they're sending out the data at like 60 gigahertz or something faster. Sure. Okay. Cool. Any other thoughts to this? Any other? Sure. Cool. So let's return back to the slides. Let's see what it looks like. Yeah. Good stuff. Yeah. So actually, this is good. So here we can see the range trade-off. So Bluetooth operates in the actually, I kind of disagree with this. Okay, actually, this doesn't fully support my point, but I'll it's for a different reason. I'll get back to it. Okay, that's fine. Yeah, good. So Wi-Fi can communicate at a bunch of different frequencies. Bluetooth is generally just 2.4 gigahertz. Good. It's good. This is different. It's fine. Okay. It's good. Sorry, just looking through. Guess. Oh, yeah. That's okay. All right. Good. It's fine. It's fine. It's fine. Okay. This is what I want to show you. Good. So here is actually every single possible band that is allowed for a Bluetooth like signal. And you might be kind of surprised because it's actually like very small. There's only like 40 possible frequencies that are allowed. And you can notice that each frequency only has a 2 megahertz spacing. So that means that if I zoom in here, so if I were to send out data using 2,410 megahertz, and now if I wanted to send out data on like the next higher frequency, it would just be like 2 higher, it'd just be 2,412 megahertz. So our receivers need to be super fine-grained in order to properly tell apart something that is just like it's less than a percent different in frequency, which is kind of cool. But our hardware is able to do that. But the issue though is, well, what happens now if we have two devices that maybe at the same time they wake up at the same time and they both decide they pick a random channel that they want to transmit on. Maybe at the same time they say, okay, I want to transmit on the 2404 megahertz band. So they both start advertising on that at the exact same time. And that's probably going to be fairly common, right? Because we only have 40 channels total. Like I said, there's probably thousands of Bluetooth devices within a tenth of a mile here. So okay, what happens in that case? What if two devices, try to broadcast on the same channel? What's going to happen? Okay, yeah? Yeah, so unfortunately, there's just major contention, and the signal will not get through, and the data will be corrupt, and so you will need to, realize maybe a device as it's sending out data, maybe it will also be reading in data, and we'll realize, oh no, I'm actually receiving another bit of data that's on the same frequency channel, therefore I'll stop sending things out and I'll send an error message. Yeah, this is a big problem. Okay, well, how do we now, let's say a device has just had that. So a device has just tried to send out over the frequency band of 2404 and it failed. Okay, what does it do next? Yeah? Yeah, perfect. So now we can just try a different frequency. Should we go maybe like just try the next frequency up, or should we do a different strategy? What do you think? Yeah,
Probably it, right? And if you had contention with something else,
absolutely. Yeah. So we actually don't want to just try the next frequency up in any sort of like um, predictable pattern. Instead, we want it to be as randomized as possible, so that every device, in theory, like has the best chance of accessing an open channel. So yeah, if you have two devices that have contention on the same wire, then they are on the same band, then they will both probably stop transmitting on that band, and then they will put two new random bands, and then they will start transmitting on that frequency now. Yeah. Well, there is also a slight issue. Okay. If we look at this, as I mentioned, so Wi-Fi actually also shares the 2.4 gigahertz spectrum. And well, this is quite unfortunate because actually the Wi-Fi bands, you can see, are much wider. This is not good because now there are, in like actuality, especially if you have like multiple Wi-Fi signals all happening at the same time, maybe multiple Bluetooth signals, maybe instead you only have access to, what is that, like 9 actual regions at once. You no longer have access to like all 37 regions. Yeah, this is not great. So this like context switching sort of thing, or what's the official term for it? It's like yeah, frequency hopping. That's right. So this frequency hopping strategy is absolutely crucial in order to make sure that every device is properly able to send out its data. Okay. Now another question for you. So let's say I just connected to my headphones. Maybe it just sent out data on 2404, okay, and I properly received it, and it's all good. The next time my headphones want to send out data, should it stay on 2404? So let's say it just had a valid transmission on 2404. Should it stay there, or should it move to a different frequency band now? Yeah.
probably stay, right?
So actually, it's just going to hop every single time. So every single time that you send out data over Bluetooth, it's actually going to pick a different frequency band. Yeah, it's always going to be hopping. What that means now is if you have a Bluetooth device, every single channel needs to be constantly sniffed. Like if you have a receiver, every single channel needs to be sniffed, and all of the data needs to be parsed and read in. And then what will happen is there's going to be some identifier on each one of these packets. Maybe the identifier will have like an ID. I guess that's what an identifier is. So it will have an ID that is like this ID, maybe like hex 2357 denotes that these are Ethan's headphones or something. So what you have to do is you have to sniff every single packet coming in and then figure out which incoming packet is actually the one that I care about. Because you're going to be receiving packets from everyone's headphones and mice and things. But there needs to be some sort of operating system thing that tells you, which device is actually the one that you care about. Okay, cool. Good. Yeah, question.
Is there any kind of like security, like what's stopping you from listening to someone else?
Yeah, so you can absolutely see everyone's incoming data, and this is crazy. Actually, great point. So you can see everyone's data coming in. This also is the same thing though for Wi-Fi. You can also see every single bit of internet traffic that is being sent through the air. Like right now, like on your computer, if you want, you could just see every single bit that's being sent out of my computer, out of like the dean's computer. You can see every single bit of information. Why is that actually okay though? Yeah. Yeah, exactly. So what will happen is the data, maybe before it's sent out, is it goes and encrypts it. So it sends out basically just looks like a bunch of random ones and zeros, and then the receiver will go and decrypt it. Yeah, and this goes for Wi-Fi and Bluetooth. There's actually several layers of encryption that exist. So there will be a layer of encryption on the hardware level. This encryption is like really bad though. It's if you've ever has anyone connected like a Bluetooth keyboard, and in order to like connect to the keyboard, you need to press like a 4-digit code or something? Anyone seen this before? Yeah. That, like, you're not going to believe me, that was actually all of the security that Bluetooth originally started with, was just a 4-digit code, which is crazy, right? Because that would take like a minute to crack, right? That is starting out, that was the only security that Bluetooth came with. And then later, they realized that this is later, like Bluetooth device manufacturers realized that this was a bad idea. So then Bluetooth device manufacturers all like came up with their kind of own proprietary method of encryption. So there's actually not like in the Bluetooth standard, there's actually not a standard way to encrypt packets other than that just like 4-digit code right there. Everything past that is like some sort of proprietary encryption method. Yeah.
So everybody has their own encryption method. How does it know how to decrypt?
Yeah, it's just like if you have headphones that you connect to, and maybe you have to download an app or something, and the app will now download the proper drivers and will figure it out. Yeah, or yeah, you can like maybe the most secure packets. Maybe if it's like a keyboard, maybe the most secure things, only that part will be encrypted or something. It's completely up to the developer of the peripherals and yeah. Question.
So if there's only 37 data channels,
Mm-hmm.
you only have like 37 currently active devices.
Yeah, absolutely. So you can only ever have at one point 37 Bluetooth devices that are actively transmitting out data. But that's actually generally okay because your Bluetooth packets will take like a millisecond at most, potentially even like a few microseconds. They're going to be so quick, it might just be like, I pressed a key on your keyboard. Like, oh, I moved your mouse by this much. It's like, oh, I did this. And that's like instantaneous. Yeah. Headphones, yeah, they sending out, that's going to be like a little bit more intense on your frequency band. But yeah, that'd be interesting. I wonder if you bought like 200 headphones, like at what point like they would all just stop working because they're all just trying to like send out data on this band. If you have like 200 mice, I bet that would still be fine because yeah, the packet size would be so short. Yeah, great question. Sure. Also note, let's see how much time. Okay, so also note that there are these green bands right here, and these green bands, these are for advertising, because as I showed you at first, what I showed you at first was all of the devices that my iPhone could see, but actually I believe all my iPhone could see was actually just all of the advertising channels. All my phone was looking at was just what devices were advertising their like model number and things. Because yeah, each Bluetooth device will need to advertise itself in order for someone to connect to that device. And the advertisements maybe take like, yeah, it'll send out a super quick packet. It'll be like, this is my name and I'm ready to be connected to, which will take like, yeah, a millisecond at most to send out that packet. So it's okay that there's only like 3 bands total because those packets are just so short. And yeah, but it is kind of interesting too. Like you can't have, yeah, there's a limited number of devices that can like at one point be advertising themselves, but also yeah, it happens so quick. But sure. Good. I think I don't know. I can show this. Let's see. Sure. So the peripheral every once in a while will send out an advertisement, and I guess it takes less than 10 milliseconds. No, is that right? 150 microseconds? Yeah, okay. So I guess the advertisement is just 150 microseconds. So super fast, like basically like a tenth of or a sixth of a millisecond. And then maybe like every 10 milliseconds or so, it will send out like another advertisement signal. So it'll just keep every 10 milliseconds, it'll send out another advertisement, another advertisement, another advertisement. But that's such a short signal that it won't really affect anything. Yeah. Cool. All right. That's probably good. Yeah. Any other questions on this? So today's lecture, I guess, was mainly on just kind of like the analog characteristics and kind of just the conceptual understanding of what happens like in the air around you with Bluetooth and the frequency channels and things. When you do your Bluetooth project for Lab 4, which I believe is due next week, for the most part, you actually don't even need to worry about any of this because all you have to do is just say, oh, like advertise this ID and then go and grab these packets out and you're done. Because yeah, what's really nice is you have Bluetooth like embedded in your ESP32 itself. Like there's just Bluetooth like inside of, like you can even see the antenna. The antenna is like little squiggly part that's on the top of the ESP. And so that is the antenna that I was talking about, the like big rod that's just sniffing the air for electrons. And then yeah, there's a Bluetooth controller, and then there's an operating system that adds this nice like layer on top, this nice software layer on top, to where you can just deal with like IDs and like handlers and things, and you don't have to worry about sending them to the individual bits. But maybe you're going to go and work for like Qualcomm, very possible, and then maybe you'll need to make your own frequency hopping algorithm at some point. Pretty cool. Sure. Okay. Any final questions on anything? I forgot to post the quiz last weekend. I deeply apologize for that. I know you were really beaten up about that. There will be a longer quiz this weekend. It will be 10 points instead. It will cover I squared C all the way through today's lecture through Bluetooth. So look out for that. I'll try to post it hopefully today so that you have a little bit longer. If there are no more questions, then we can get out a little early. Thank you.